Yes, good evening to all. Okay, ma, I am going to start. The next topic is I pattern. One way to study the intersymbol interference in a PCM or data transmission system experimentally is to apply the received wave to the vertical deflection plates of an oscilloscope and to apply a sawtooth wave at the transmitted symbol rate r equals to 1 by t to the horizontal deflection plates. So, to study the intersymbol interference, apply the resulting wave to the vertical plates and sawtooth wave to the horizontal plates. Then we can study the intersymbol interference. By applying like this the resultant waveform to the vertical and sawtooth to the horizontal plates, the waveforms in successive symbols, that is in t is equals to tb intervals, translated into one interval on the oscilloscope display. So we are applying so many symbols, but those will appear on the oscilloscope display in the interval t is equals to tb for the case of a binary wave. The resulting display is called an human pattern. So the resulting display is called an eye pattern because of its resemblance to the human eye for binary waves. So if first bit is transferring, it is 1 like this. If the first bit is transferring, if it is 1, then it will be like this in between 0 to t or tb. If the second bit is 0, then it will be like this. Again third bit is, if it is 1 like this, 0 like this. The bits are displayed on the oscilloscope display or looks like an eye of human. That's why this pattern is called as eye pattern. Very simple, ma. So why this is called as eye pattern? It resembles the human eye. That's why it is called as eye pattern. When we are sending the binary bits, those bits will be displayed on the oscilloscope display in the interval 0 to tb, which looks like an eye of human. Okay. So what is the width of the eye, height of the eye? That we are going to see now. The interior region of the eye pattern is called the eye opening. So this is called as eye opening. See here, this is the example, binary wave 1 0 1 1 0 1. So 1 1 1 zeros, 2 zeros at the downside, 4 ones at the top side, 1 1, sometimes 1 like this also, sometimes 1 like this also. So 4 ones, 2 zeros. For this data, the eye pattern is like this in the interval 0 to t. See, tv. So this is called as eye pattern, which is looks like eye of human. Okay. So interpretation of eye pattern. So what is the width of the eye? What is the slope of the eye? What is the height of the eye? How we can indicate these? So interpretation of eye pattern, very important for 6 marks, guys. Okay. So this is the best sampling time period, and this one is the interval over which the wave can be sampled. This is the sampled wave okay, interval of the sampled wave, and this one is the margin over noise, and this one is the distortion at sample time, and this is the slope which is equals to the sensitivity to timing error and this one is also distortion of zero crossing. So two types of distortion, this one is at sampling time and this one is when zero crossings are appearing, axis crossings, there also will get the distortions. So two types of distortions, and this one is the height of the eye, this one is the width of the eye, and this is the slope of the eye. This is the interpretation of eye pattern, very simple interpretation of eye pattern. Okay, so here same explained here also, the width of the eye opening defines the time interval over which the received wave can be sampled without error from intersymbol interference. Okay, and second one is the sensitivity of the system to timing error is determined by the rate of closure of the eye as the sampling time is varied. So when the sampling time is varied, rate of the closure eye, this is the closure eye as the sampling time is varying, is called the slope. The height of the eye opening at a specified sampling time defines the margin over noise. So this one is the margin over noise, which is equals to the height of the eye. So this is about the eye pattern. In this we have only two topics: eye pattern, by which we can study the intersymbol interference, and the next one is the interpretation of eye pattern. Intersymbol interference already discussed that's why I am not touching it. What is intersymbol interference? Okay. Okay, next topic is the correlation receiver. Correlation receiver So this is the correlation receiver. So only 5 members are there. Who are there May I know? My voice is audible to you 15. Okay, now it becomes 50. Suddenly 10 members joined. Sheikh Muhammad Hussain. Okay, Hussain, very good. Vanita, okay. First time I am seeing Sheikh Muhammad Hussain. Srinath, okay, very good. Correlation receiver which is important. If the paper is tough, you will get the questions of these topics questions from these topics: correlation receiver, okay, matched filter and correlation receiver. So very simple if you practice. Yeah, Sushita, you are also there. Okay So correlation receiver. What is this correlation receiver? So we know that for an additive white Gaussian noise channel, and for the case when the transmitted signals are S1 of t, S2 of t and so on Sm of t, the optimum receiver consists of two subsystems. So here if the channel consists of additive white Gaussian noise and the signals are like this, the optimum receiver or correlation receiver consists of two subsystems. So correlation receiver is divided into two types: detector and vector receivers. Consists of two subsystems. What are the two subsystems? Detector and vector receiver. So what is detector and what is vector receiver? The detector part of the receiver is shown below This one is the detector part of the receiver. Detector part of the receiver. Here x of t is the input signal and x is the observation vector. This input signal is given to the product modulator and integrator. The combination of these we can call it as correlators. Correlator product modulator and integrator combined we can call it as correlators. Okay, And what is the operation of this one? Pi 1 of t, pi 2 of t, and so on. Pi n of t, here we are representing the basis functions as n and input signals as m, energy signals. Okay. So, and here observation vectors are n number. So, what is the function of this one? So, this is the diagram for detector, and we have vector receiver also. So, here it consists of a bank of m product integrators or product integrators, commonly call it as correlators, supplied with a corresponding set of coherent reference signals or orthogonal basis functions. These are supplied with the set of orthogonal basis functions pi 1 of t, pi 2 of t, and so on, pi n of t, that are locally generated. So, which we will generate locally these basis functions. This bank of correlators operate on the received signals. So, which is the received signal here? X of t, that is the input signal. These operated on the received signal x of t in the interval 0 less than or equals to small t less than or equals to capital T to produce the observation vector x. So, these are all operated, correlators are operated on the x of t to get the observation vector x. Okay. So, this is the write up mark. And the second part of the receiver is the vector receiver, which is shown in below figure. This is the vector receiver. Second part of the correlation receiver is vector receiver, and here the input is the observation vector x. Okay, and this is the second part of the correlation receiver. So, what is the function of this one here? So, it is implemented in the form of a maximum likelihood detector that operates on the observation vector x. So, here this is the observation vector x. This will operate on the observation vector x to produce an estimate m cap, here to produce an estimate m cap. So, all this vector receiver is operated on the observation vector x to produce an estimate m cap. So, how can we get estimate m cap of the transmitted symbol mi, where small I is varying from I to capital M, energy signals, in a way that would minimize the average probability of symbol error. So, here we are going to transmit the symbol in such a way that the probability of error will be less. Okay. So, next, the n elements of the observation vector x are first multiplied by the corresponding n elements of each of the m signal vectors. See here, these m signal vectors are individually multiplied with the observation vectors, corresponding observation vectors, and the resulting products are successively summed in the accumulators. So, this is the accumulator which will sum the resulting products are successively summed in the accumulators to form the corresponding set of the inner products. So, what are the inner products? X comma S1, X comma S2, X comma Sm. These are the inner products. These will available in the accumulator. After getting these products, the inner products are correlated for the fact that the transmitted signal energies may be unequal. Here, each and every signal may be not the same energy. That's why the energy signal we are giving it as E1, E2, and so on, En. Okay, and sum these two to get the estimate of M cap. Okay, the optimum receiver is commonly referred to as a correlation receiver. So, here how can we select the, after summing this with this, we will get some values here. Select the largest value which will give the estimate of M cap, which is equals to the estimation of M cap. So, this is about the vector receiver. So, first one is the detector. Receiver consists of two parts, detector and vector receiver. From the detector, the input signal is converted into the observation vector. In the vector receiver, the observation vector is converted into the estimate M cap, which is the largest value of the resultant vector receiver. Two parts. Okay. So this is the write-up of the correlation vector. The optimum receiver is commonly referred to as a correlation receiver. So don't confuse what is correlation receiver, what is optimum receiver, both are same. So the optimum receiver is commonly called it as correlation receiver. So both are same. And what is matched filter receiver? So the special type of optimum receiver is known as matched filter receiver. So what is matched filter means? The special type of optimum filter is known as matched filter receiver. Okay, now, so what is matched filter and what is the block diagram of the matched filter receiver, that we are going to see now. Okay, so for that, first of all, let us assume that pi 1 of t, pi 2 of t and pi n of t are 0 outside the interval 0 to t. So, in the interval 0 to t only, the basis functions pi 1 of t, pi 2 of t and pi n of t are present, which are 0 outside the interval. So, this will help to get the expression for the maximum signal to noise ratio of matched filter. Okay. So, now, so here, which is like theorem, okay, which is like theorem, we will assume and we will get the signal to noise ratio expression of the matched filter. Okay, so you need to remember how we are approaching. First of all, we need to consider the basis functions which are 0 outside the interval 0 to t. After that, what we have to do now, again consider a linear filter with impulse response hj of t. Consider the linear filter impulse response as hj of t with the received signal x of t used as the filter input. So what is the filter input here? X of t. Impulse response we are considering as hj of t, and the output of the filter we are considering as yj of t. Okay. So x of t is the input, yj of t is the output, and impulse response of the filter we are considering as hj of t. Impulse response generally we will call it as h of t. Here we are considering as hj of t. Okay. Next, the resulting filter output yj of t is defined by the convolutional integral. You know very well about this expression. No? How can we write the expression for the filter output in terms of impulse response? Yj of t is equals to integral minus infinity to infinity x of tau into hj of t minus tau into d tau. This is from signals and systems, ma. Okay. You have to remember all these equations, how we are writing. Okay, practice for 2 to 3 times, then you can able to remember. Okay. Now set the impulse response hj of t is equals to pi j of t minus t. Take this expression as 2. Now set this impulse response to pi j of t minus t. Then the resultant filter output is, in place of hj of t, we have t minus tau. So here t minus t plus tau. Pi j of, in place of t here we have t minus t, and minus of minus you will get plus. Okay. Understood now this expression how we have written? T minus t. In place of t what we have here? T minus tau. So capital T minus t plus tau. Pi j of capital T minus t plus tau. Just substitute this in this one. Okay, according to this relation into d tau. Sampling this output at time t is equals to capital T, we get wherever small t is there, put capital T. So yj of t is equals to integral minus infinity to infinity x of tau into ij of, if you substitute capital T here, this will get cancelled, will get only tau into d tau. Next step, we assumed one condition now, pi j of tau is equals to 0 outside the interval 0 to t. So finally, only for 0 to t we will get this expression. For remaining interval it is 0. Hence yj of t is equals to integral 0 to capital T x of tau into pi j of tau into d tau. Take this one as expression number 5. Am I going too fast, ma? Are you able to writing the expressions? Okay, I will move because we don't have much time. Already it is 8:30. In 30 minutes, I have to finish so many topics. A filter whose impulse response is a time reversed and delayed version of some signal pi j of t, as in expression number 2. This is the expression number 2 ma. So from that we are mentioning this note. Okay, next. Correspondingly, the optimum receiver based on the detector of figure which is shown in below is referred to as the matched filter receiver. So previously in the correlation receiver we have the detector and vector receiver, and here this is a special type of optimum receiver, hence the detector is changed. The detector is changed like this ma, okay, and vector receiver. Every receiver consists of two parts, detector and vector receiver, and here the detector part is changed and the vector receiver is same as the previous correlation receiver. So what is the detector of the matched filter is received signal x of t, and here pi 1 of t minus t, pi 2 of t minus t, pi n of t minus t, and here switch is there to sample at t is equals t, and here you are getting the observation vector x. So detector part of the matched filter receiver. For a matched filter operating in a real time to be physically realizable, it must be causal. So this is the one more assumption. Hence, to get the system, the matched filter to be causal, its impulse response must be 0 for negative time. Hence, whenever hj of t is equals 0 for t is less than 0. This is one more assumption. Okay. So up to now we have defined what is the detector and what is the matched filter receiver and what is the output expression, what is the input, what is the impulse response of the filter. Now we are going to derive the expression for signal to noise ratio, that to maximization of output signal to noise ratio of matched filter. So here this is also derivation ma, we need to take some assumptions to get the signal to noise ratio derivation. Okay, consider a linear filter of impulse response h of t with an input that consists of a known signal pi of t. Here also we are considering the linear filter impulse response as h of t with an input that consists of a known signal pi of t. Here we are considering the input as pi of t and an additive noise component w of t as shown in below figure. So this is the pi of t known signal, this is the x of t out input to the impulse response filter, and this is the white noise. So this is the impulse response h of t and this is the output y of t, which is sampled at time period t is equals t. So we may write x of t is equals to pi of t plus w of t, 0 less than or equals to small t less than or equals to capital T. Take this one as again expression number 1, where t is the observation instant. Now we may choose pi of t to be one of the orthogonal basis functions. Generally we are assuming as pi functions as basis functions, that you know very well. The w of t is the sample function of a white Gaussian noise process of zero mean and power spectral density is n0 by 2. This is also you know very well. We have discussed so many times. Since the filter is linear, the resulting output y of t. So if the filter is linear, the output is expressed as y of t is equals to pi naught of t plus n of t, where pi naught of t is the output produced by the signal, because signal is pi of t. So pi naught of t is the output produced by the signal, and n of t is the noise components of the input x of t. Okay. A simple way of discovering the requirement that the output signal component pi naught of t be considerably greater than the output noise component n of t. So here, to have the filter better, we should choose the output signal component should be greater than the noise component. Okay, the output component should be greater than the noise component. So which will be measured at time period t is equals to t as large as possible compared with the average power of the output noise n of t. Okay. So how can we write the expression? Signal to noise ratio of output is equals to, this is the signal power and this is the noise power. Signal to noise ratio, signal power and noise power. So now this is the output signal to noise ratio basic expression for any receiver. So signal energy by noise energy. Now we are going to get the expression of this one, signal energy and noise energy. Substitute those two in this, we will get the expression for the signal to noise ratio at the output. So this maximization occurs when the filter is matched to the known signal pi of t at the input. When the filter is matched, then only we will get the signal to noise ratio as maximum. So how can we achieve this one? Try to follow step by step. Let pi of f denote the Fourier transform of the known signal pi of t. If the signal is pi of t, the Fourier transform is pi of f. And h of f denote the transfer function of the filter. So these are the assumptions again. In the Fourier transform of the output signal, pi naught of t is equals to input multiplied by the transfer function, that is h of f into pi of f, and pi naught of t is itself given by the inverse Fourier transform. So hence the pi naught of t expression will be given as inverse Fourier transform of pi naught of t, which is equals to pi naught of t is equals to integral minus infinity to infinity h of f into pi of f into e power j 2 pi ft into df. This is again from signals and systems background. Okay, how can we write the inverse Fourier transform? Here, when the filter output is sampled at time t is equals t, we may write whole square. We are writing here this whole square, and in place of t we have substituted capital T, whole square we are considering, whole square here, whole square here. This is the expression here we are writing. Take that one as expression number 5. Consider next the effect of the noise W of t alone on the filter output. Now consider the effect of the noise W of t alone on the filter output. Now the power spectral density Sn of f of the output noise N of t is equal to the power spectral density of the input noise W of t times the squared magnitude of the transfer function h of f. So here the power spectral density of output noise Sn of f is equals to the power spectral density of the input noise times transfer function squared times the squared magnitude of the transfer function h of f. This sentence we made it like this. Since W of t is drawn from a process that is white with constant power spectral density N naught by 2, it follows that Sn of f is equals to power spectral density of white noise is N naught by 2 mod h of f squared. Take this one as expression number 6. The average power of the output noise N of t is E of n square of t is equals to integral minus infinity to infinity into power spectral density, that is Sn of f into df. Substitute this in this, you will get this one. Take this one as expression number 7. Now we have E of n square of t, that is 7, and fifth expression is this one, mod pi naught of t whole square. Substitute these two in expression number 3, which is the signal to noise ratio at the output. So rewrite the expression, we will get like this. So now to find the solution to this optimization problem, apply the mathematical result known as Squarge inequality to the numerator of this equation. Numerator of this equation, what is the Squarge inequality? See this one, integral minus infinity to infinity mod h of f into pi of f into e power j 2 pi ft into df whole square is less than or equals to integral minus infinity to infinity mod h of f square into df into integral minus infinity to infinity mod pi of f square into df. Take this one as expression number 9. Using this relation in 8, you may simplify the output signal to noise ratio as, if you substitute this as the numerator and the denominator also you are getting something. So that this expression, that expression, this one will get cancelled. Okay, we will get 2 by n naught and this expression which is integral minus infinity to infinity mod pi of f square into df. Take this one as expression number 10. Now the right side of above expression is defined by two quantities. This one is defined by two quantities, that is the signal energy is given by, this is from the Rayleigh expression. So this is from the Rayleigh density function. So what is the Rayleigh's theorem means? Here The signal energy integral minus infinity to infinity, integral minus infinity to infinity, which is equals to pi of t is equals to pi of f. This is from the Rayleigh's theorem. This is from the Rayleigh's theorem. You have to note down there from Rayleigh's energy theorem. These are the expressions. Rayleigh's, R-A-Y-L-E-I-G-H. Rayleigh's Rayleigh energy theorem. This is from the Rayleigh's energy theorem. This expression is equals to this expression. Okay. Next, the noise power spectral density is N0 by 2. So these are the two. So what is this and what is this? This is the signal energy and this is the noise power spectral density. Next, the right side of equation 10 does not depend on the transfer function h of f. By seeing, you can say that there is no question of transfer function h of f. Okay. Consequently, the output signal to noise ratio will be a maximum when h of f is chosen so that the equality holds. So here, the signal to noise ratio, to get the maximum value, replace consider this equation to equality principle. So equality holds, that's why consider equal expression. Signal to noise ratio output maximum is equals to 2 by n0 into integral minus infinity to infinity mod pi of f squared into df. That is expression number 11. Next, for this condition, h of f assumes its optimum value denoted as h optimum of f. So here the filter is assumed the filter function as optimum transfer function as h optimum of f. Okay. Next, from the Sparge inequality, the optimum value of this transfer function is defined as h optimum of f is equals to pi star of f into exponential of minus j 2 pi f t. Take this one as expression number 12. So here this entire thing is practice. This is from the knowledge of signals and systems. We have one system, we have one receiver, we are going to derive a transfer function, what is the input, what is the output, what is the power spectral density, what is the signal to noise ratio expression. Okay. So it is somewhat like theorems. Okay. Where pi star of f is the complex conjugate of the Fourier transform of the input signal pi of t. This relation states that except for the necessary time delay factor this, the transfer function of the optimum filter is same as the complex conjugate of the spectrum of the input signal. This one is equals to this one except for this expression. Okay. So equation 12 specifies the matched filter in the frequency domain, and to characterize it in the time domain, we take the inverse Fourier transform of h optimum of f in equation 12 to obtain the impulse response of the matched filter as. Take the inverse Fourier transform for equation 12, then we will get h optimum of t is equals to integral minus infinity to infinity pi star of f into e power minus j 2 pi f into t minus t into df. Since for a real value signal pi of t, we have pi star of f is equals to pi of minus f. This you know very well. This is also again from the concept of signals and systems. Complex conjugate is equals to pi of minus f. Then h optimum of t is equals to integral minus infinity to infinity pi of minus f into e power minus j 2 pi f t minus t. So here in place of pi star f, we have substituted just pi of minus f. From this, again the expression can be replaced as pi of t minus t. H optimum of t is equals to, this total expression can be replaced as pi of t minus t. This is also from signals and systems. From signals and systems. Okay. So now equation 13 shows that the impulse response of the optimum filter is a time reversed and delayed version of the input signal phi of t. That is, it is matched to the input signal. So same we have considered in the matched filter also, not time reversed, okay, and delayed. Time reversed and delayed. Hence it is matched to the filter. Now properties of matched filter. So we have 4 properties for the matched filters. Very easy ma, very important also. Properties of matched filter, 4 properties. First one is the spectrum of the output signal of a matched filter with a matched signal as input is, except for a time delay factor proportional to the energy spectral density of the input signal. So this is the property. What is the proof? Let pi naught of f denote the Fourier transform of the filter, output pi naught of t, then pi naught of f is equals to transfer function multiplied with input. This already we have, okay, pi star of f into e power minus a 2 pi f into this we have here. Then pi naught of f is equals to pi star of f into pi of f, you can write it as mod pi of f square into e power minus a 2 pi f t. So this property is satisfied. Proportional to the energy spectral density. So this is the energy spectral density of the input signal. Okay. And property 2. The output signal of a matched filter is proportional to a shifted version of the autocorrelation function of the input signal to which the filter is matched. So here you don't have any proof in the textbook now. They have given only 2 lines for the proof. So you should go through this material. Same expression we have considered pi naught of f. From this we can write h of tau f, substitute this, then you will get pi naught of f like this. Then take the inverse Fourier transform, you will get like this, and pi naught of t is equals to this one, and then you will get this one by taking the common e power j 2 pi f. We know that the energy spectral xi of w is equals to this one. This is also from, again, from which principle? Can any idea? Do you have any idea about this expression, energy? Any one of you? Okay. The energy spectral density xi of w is equals to mod pi of f whole square. Take this one as expression number 16. Autocorrelation is vice versa to the energy spectral density. Okay. Next, autocorrelation function, you know very well, which is given as integral minus infinity to infinity energy spectral density into e power j 2 pi of tau into df. In place of this, we have substituted expression number 16, then you will get this one. From 15 and 17, we can write pi naught of t is equals to r of t minus t. If you compare 15 and 17, ma, so this is the 15, in place of tau we have t minus t. So that is the expression. Now at t is equals to 0, I am so sorry, not able to move properly. Yeah, we know that autocorrelation function is maximum at tau is equals to 0. So r of 0 is equals to e, which is equals to the energy of the signal, which is equals to pi naught of t. Okay. Next, property 3. The output signal to noise ratio of a matched filter depends only on the ratio of the signal energy to the power spectral density of the white noise at the filter output. So here the output signal to noise ratio of a matched filter depends only on the ratio of the signal energy to the power spectral density of the white noise. So signal energy divided by, this is the power spectral density of white noise. So how we will get? So you know that this expression for maximum signal to noise ratio, at small t is equals to capital T, maximum value of the filter, output at t is equals to integral minus infinity to infinity mod pi of f into df is equals to this one, which is equals to E, again from the Rayleigh's energy theorem. Okay, then this can be substituted as capital E. So this can be written as capital E divided by n naught by 2, which is satisfies the E is the ratio of the signal energy to the power spectral density of the white noise. Okay, that is about the property 3. And next one is the property 4. The matched filtering operation may be separated into two matching conditions. Here we have phase matching condition, amplitude matching conditions. Okay, phase matching conditions that produces the desired output peak at time t. Spectral amplitude matching conditions that use this peak value as its optimum value signal to noise density ratio. Okay, so here phase matching, amplitude matching. In polar form, the spectrum of the signal pi of t being matched may be expressed as like this. You know very well in terms of magnitude and phase. Where this one is the amplitude spectrum and T of f is the phase spectrum of the signal. You know very well how to define the signal in polar form, magnitude and phase. The filter is said to be the spectral phase matched to the signal pi of t. If the transfer function of the filter is defined like this, then only we can say that the signal is matched to the filter. Okay. So where mod h of f is real and non-negative and t is a positive constant. The output of such a filter is, we can write it as pi naught of t dash is equals to integral minus infinity to infinity. This like this you can write, and the same expression can also be written like this. Wherever t is there, here we have substituted in place of t, t minus t, where the product is real and non-negative. Okay, here it is converted into phase, amplitude and phase. Next, the spectral phase matching ensures that all the spectral components of the output phi naught of t add constructively at time t is equals to t. So these are some expressions. Okay, at t is equals to t. For spectral amplitude match condition, we choose the amplitude response mod h of f of the filter to shape the output for best signal to noise ratio at t is equals to t by using. So use this condition to get the best signal to noise ratio for the filter. So that's it about this topic. Only 10 members, 15 members, B and C sections, very bad, very low strength. A section people are doing well, I heard that. Your strength is very low, I don't know why. Okay ma'am, so with this eye diagram and matched filter is completed. Next we have cosine raised spectrum. So if time permits, we will complete it in offline mode. Otherwise, I will take one more class for this raised cosine spectrum and TDM, time division multiple access. So these two topics are pending. TDM is from first unit and raised cosine spectrum from second unit. Okay. So I think, shall I wind up now? 9 members are there. Hope at least one will give the reply. Okay ma, I am going to end this session. Okay, thank you madam. Yeah ma'am. Okay ma, Muhammad Hussain, thank you very much for your response. Anyway ma, I am going to end this session. Thank you. Good night all. Bye.